Well, good morning, everyone. My name is 𝗦𝗧𝗕𝗦𝗬𝗓. I am the Process Optimization Specialist for Lakeside Controls. This is the ninth episode of a series of webinars I've had throughout this year. And today we're going to talk about split range control. So a couple of guidelines first. Your microphones are off. You will be able to ask questions via either the chat box or the Q&A. If you could just use the Q&A, that'd be great. That should be on your screen. Um, you can ask questions anytime during the presentation, and I will answer them at the end. And now there is a 10-second time delay between the moment I speak and the moment you hear me. So it's if light travels at 300,000 kilometers a second, that means I'm 3 million kilometers away from you. This is where I'm broadcasting from. Actually, I'm not in Mississauga. I'm broadcasting from my third counter of the Close Encounter of the Third Kind spaceship. Your questions are anonymous. Only I can read your only I can see your questions. So don't be shy. I encourage questions, and I will read the question out and answer them. And if you think of a question afterwards, or if you don't have time or whatever, you can always contact me via these coordinates. Cell phone is best. Email is best. Don't try to reach me at the office because I'm rarely at the office. And this is part of a series of lunch and learns. So you can see number 9. So that series, and if you are interested, you can contact me. All of these have been recorded, and therefore you can get. I can send you the links to actually the previously recorded webinars if you're interested. As I said, this is being recorded, and a link to the recording will be sent to you after this presentation. A bit of a safety moment. Obviously, it's middle of November, and it's amazing looking outside. Well, I'm not. I'm in my spaceship. I can't be seeing trees. But last time I was on planet Earth, I saw a lot of trees still have their leaves at the middle of November, which is quite amazing, actually. But obviously, time change, winter coming, summer, winter solstice. There'll be a lot of driving at night, so it's very important to a lot of risk increases when you're driving at night. It's important then to not to first thing not to overdrive your headlights. So don't drive faster than you can see with your headlights. Make sure your headlights are properly aimed. Uh, don't follow vehicle too close. You might blind them and so forth. So just be obviously a lot more vigilant when you're driving at night. A little bit about Lakeside. Uh, so it's over actually with probably more than 325 employees right now. Probably I think we're 350 or something like that. We just had a bit of a hiring spree. Been founded since 1952. We can trace our roots back to 1952. 8 service centers. I believe actually that's going to increase. We just got a new building in Dundas, Ontario, and where we'll be doing a lot of our assembly and our manufacturing there. Reason being, at Lakeside and all the Emerson Impact partners are taking over the valve service portion that was actually taken care of by Emerson, and with the exception of nuclear valves. And so we're taking on a lot more staff. We're transferring staff over, and we'll be actually doing the valve servicing. So we're pretty excited about that. And we've actually had quite a bit of growth in all those industries you see there. I pretty much worked in most of all of those industries right there. And as I mentioned, we are part of the Emerson Impact Partners. So Emerson decided to partner up with specific companies with specific geographical assignments. And you can see our territory starts from just this side of Kingston right to the Manitoba Saskatchewan border and part of Nunavut, and there are 21 Emerson Impact Partners, and so therefore, and the reason why Emerson does that is that they believe, and it's I think it's very true that a local presence is a lot more effective for our customer relations than having a monolithic approach where it's just one corporation trying to capture the thousands of customers that we have. And why is that? Also, if you have an issue, if you have a problem, a technical problem, a situation, we know who to talk to. We have a team inside here. We know who to talk to at Emerson to be able to provide you with a proper solution. And I've never been too crazy about this slide, but it's you can see we do sell obviously all sorts of instrumentation, analyzers. We have valve regulators, control valves, different types of control valves, on-off valves, isolation valves, control system. We got the 𝗩𝗘𝗦𝗜𝗧. We have Ovation. We provide all sorts of services, training services, either product training or just generic training, as you'll see in a little bit. We do manufacturing, we do assembly, and so forth, and consulting as well. And the whole idea is we provide you with a good customer experience. I think at the bottom of our email signature, there is a clickable icon where you can talk, you can give us feedback. I always say any feedback is good feedback, and we are striving to provide you with a positive customer experience. A little bit about myself. I've been doing process control, consulting, troubleshooting, tuning, training for over 30 years now. And I also have a couple of gentlemen here. Andrew is actually now become my supervisor, believe it or not. He helps me out once in a while. Is very, very knowledgeable. And Dean as well, very knowledgeable. I think they both have more than 12 and 10 years experience. And some of the services, obviously, I go to site and tune some control loops, troubleshoot control loops, and so forth. I'm also responsible for advanced controls, model predictive control, and neural net. I also do DCS alarm rationalization services. And the idea there, 8 out of 10, 80% of your alarms, if any of you are in production, uh, probably take a look at your alarm banner in your control room. I would bet you that it's probably full. And 80% of those alarms are caused by 10 sources or less. So there's a lot of nuisance alarms. And that's what happens when you cry wolf too often, is that we tend to ignore alarms, and that's when bad things happen. So we're there not to eliminate alarms, we're there to make alarms relevant, and reduction of alarm floods, such as if a pump trips, do not alarm a low flow, do not alarm a low pressure, because they are redundant. Just allow the operator to focus on the root cause of the alarm. And that picture you see there is actually not a Google picture. It's actually a real picture that we took at a control room just to silence a particular alarm during a shutdown. And I do have training courses. I have basic instrumentation course and process control techniques 1 and 2, AKA loop tuning courses. And I will be putting out my schedule for 2022 shortly. Incidentally, I'm actually very, very curious if you have time to give me some feedback as to virtual versus in-person training and the advantages and disadvantages. I've been asking quite a few customers, and if you have time, I certainly would appreciate if you give me some sort of feedback on the advantages. There's the pros and cons of virtual versus in-person training, and because I have to decide which courses will be virtual and which courses will be in person. And I do have a blog that I've accumulated. If you go to our website, lakesidecontrols.com, just search for blog and Confessions of a Looney Tune. There's stories that I've accumulated over the years in terms of they're kind of humorous and not super technical, but they do have a moral to the story. So I encourage you, if you have time, to read some of the blogs. All right, now here's the good stuff. So we're going to talk about split range control. And first, we're going to define what is split range. And then we'll talk about why use split range, how to implement and where to implement split range. And then we'll finish off with a modified control strategy called a mid-range control. So what is a split range? A split range, essentially, you got one PID block that goes from 0 to 100%. And that output will go through a splitter or 2 characterizers, depending on how you arrange it. And it will take that map, that 0 to 100%. For the first valve, it will go, let's say, 0 to 50%. It will open up the first valve 0 to 100%. And then from the PID output from 50% to 100% is going to open the second valve 0% to 100%. So that is a basic split range control. It doesn't have to be just two valves. You could split it. I think the record I've seen in gas utilities is around 4 valves in parallel. But does the split always have to be 50%? Can there be an overlap? And that's what we're going to explore in this webinar, is how to properly adjust your split. Why do we have split range? A lot of times we have split range because maybe the process conditions have a high turn down ratio, meaning that sometimes summer and winter, you can think of gas utilities where we're delivering gas, and obviously we're going to be using probably less gas in the summertime than in the wintertime. So therefore we may want to, that's a high turn down ratio. Boiler startup conditions. When you're starting up a boiler, sometimes, especially large boilers, when you're idling them, the conditions of very low flow, we need to be able to control at low flow, but also at normal and high flows. Grade production rate change, grade changes, production rate changes. So we can have different production rate that will obviously affect the condition. And the whole idea is that, and we have this often sometimes when we actually have, especially engineering companies, and they know the operating conditions are going to be very, very wide. They say, can we use one valve? They're trying to save money, try to save the customer money and so forth. I understand that. But, so for one operating condition, let's say it's summer, the valve would be operating at 10%, far away from the sweet spot of a control valve. And maybe in the wintertime, you'd be operating at 90%. So perhaps then using two valves in parallel, two smaller valves in parallel, would allow you to have better control over this wide operating range. So how do you implement this? This is actually a little bit how it's programmed within my simulation. So you got a PID block coming out, and it goes to two characters. So this two characterized. They both see the same 0 to 100%. And as I mentioned, 0 to 50 will be translated to 0 to 100 in the first characterizer block, and 50 to 100 will be characterized to 0 to 100 in the second characterizer block. Now, where should you implement split range control? There's a couple of places where you can implement it. You could put it in the positioner. So you got two valves, and what you can do, especially if it's a digital positioner, but even an analog positioner, what you can do is that it receives a 4 to 20, and you can actually program within that positioner. So from 4 to 12 milliamps, 50% is 12 milliamps. From 4 to 12 milliamps, that position will command that valve to go 0 to 100%. And then you can the other valve, you could program the positioner from 12 to 20 milliamps, from 50% to 100%. It will then actuate that valve from 0 to 100%. Now, some of the issues, especially with this one, sometimes you got to be careful with some positioners have a very high input impedance. If you try to put the 4 to 20 through one positioner and then loop it to a second positioner all in one loop, it may not work because there may not be enough power to be able to power up both positioners. So you got to be wary of that. You can also do it in an I to P. Now, an I to P, as a name, suppose your valve speaks in pneumatics. It's not an electro-pneumatic positioner. It is a pneumatic positioner. Maybe a legacy valve, or for whatever application, we're using a pneumatic positioner. Now, pneumatic positioners will typically understand a 3 to 15 psi signal. Just like an electro-pneumatic positioner that accepts a current will accept a 4 to 20, a pneumatic positioner 3 to 15 psi. And what you can do here is that an I to P will convert a current signal into a pneumatic signal. And what you could do, you can actually program or calibrate, sorry, it's not digital, you can calibrate that I to P to go from 4 to 12 milliamps, 0 to 50%, will output then a pneumatic signal of 3 to 15 psi to a first positioner, and you'll have a second I to P in parallel receiving the same signal, and you can calibrate it from 12 to 20 milliamps, and it will then generate a 3 to 15 psi signal to the positioner. There's a few other permutations and combinations you can do, but that is one of them that you can actually implement. And you can also put that into your control system. And obviously, if you can, try to implement in your control system if you can. The majority of the time, you should be able to, because obviously it's clear, it's more flexible. You can adjust your curves, you can adjust your splits a lot more easily that way. So we're going to go with a live demo, but I want to have a word of caution here is that what I implemented in my simulation, I implemented the flow curve through the valve. I did not implement the actual valve position. The reason why I did that, because obviously if I go from a 0 to 100%, this is 0 to 100%, let's say, the flow is not going to follow that. The flow, the valve, every valve has a flow curve, be it a butterfly valve, be it a ball valve, be it a globe valve. And so what I did is I took 2 steps and put into one. And so into my curves, I put the flow curve into the characterizers and not the actual 4 to 20. Okay, so I got to be cognizant of that. And I do have 4 cases that I want to explore. 4 cases that I want to explore. The first case is going to be a small valve, a 1-inch valve, and a 4-inch valve, no overlap. 0 to 50, one valve opens, 50 to 100, the second valve opens. Case number 2, similar situation, a 1-inch valve and a 4-inch valve, except I'm going to have an asymmetrical overlap, meaning it's not just going to overlap in the middle, it's going to overlap a little bit sooner rather than later. Case number 3, 2 4-inch valves in parallel, no overlap. That means 0 to 50, the first valve opens 0 to 100, 50 to 100, the second valve opens 0 to 100. And then the last case is going to be a 20% overlap, or plus or minus 10%. So let me go to my simulation here. So there we go. So there's a lot of things going on here. So here you could see I got a flow controller right here. The output of the flow controller, the blue bar here is at 5%. I'm setting 5%. Graphically, this is not exactly completely accurate. There should be obviously a splitter block here to be able to split and characterize the signals to both of those, but just pretend there is one. The flow is at 5 GPM. That is the yellow value there. Here you can see I put in both flow characteristics here. So valve 1 is the 1-inch valve, in this case number 1, and valve 2 is the 4-inch valve. And you can see here from 0 to 50%, this valve, the flow will go to 100% capacity. You can see it's not a linear flow characteristic. There is nothing linear in the universe. And then from 50% onward, I'm going to start opening up the larger, the 4-inch valve. That's what I'm going to be doing. So let me bring up the trend here. Now we got a lot of things going on. So on the left-hand side, that you got the flow signal, the yellow line, and the blue line is the output of the PID. On the right-hand side, I got a green line, and that is the valve position of the small valve, valve number 1, and then the yellow line is the valve position of valve 2. Now I got to go through a few iterations here. I got to go. So let's say I put the output to 25%. 25% means now, let's take a look where we are. 25%, we're right here on the curve. That means now the split range, the valve, the flow is going to be around, let's say 71%, as we see there. But the second valve is not opening right now. And you can see the flow, obviously, it's a large output change, but the flow is smaller. We're not going to get a large flow change. So now I'm going to go, let's say, to 45%. So again, the valve, the little valve now goes to 98% open. And you can think that a valve is going to give up the ghost. At some point, any valve, once you start getting anywhere from 75% open or more, depending on type of valve, some of them are earlier, some of them are later, but the flow character is going to start to taper out. And that's why I use a flow curve here and not the actual valve position. So let me go back to here. So I've done my bump. I've moved this little valve and it's almost completely open. I'm at 45% open. So now I'm going to go to 55% open. I'm going to cross over into the big valve territory. So I got to go to 55% open. And now the big valve started to open up. And you can see now I'm getting a much larger flow change. And that is the issue when you're actually not using an overlap or even an asymmetrical overlap, is that the process will change depending on which valve you're actuating. And in this case now, any other change, if we go to 65%, now I got to have a larger change here. So the process will be different if it's less, if the output is less than 50% versus more than 50%. And one of the ways to do that is that we need to adjust the split range. So this is what I did earlier on. So these are consistently 5% output changes. And you can see here, I'm opening the small valve, and actually the valve, you can see here, it is dying off right around this point. And then now I start to actuate the big valve. And obviously it's a very, very nonlinear approach. And so this is probably the extreme case. And obviously do not do this at home, kids, okay? Do not do this at home. So let me go back now, and I'm going to go here. And now I'm going to change my case to case number 2. Case number 2, I still got a 1-inch valve right here. I still have a 4-inch valve right here. But you can see now the split is different. The split is different. So now I will, instead of achieving 100% of the flow at 50%, now I'm achieving the complete flow around 35, 40%. And you can see here also, I'm starting to open up the valve, the big valve, sooner. And what I'm trying to do is trying to even out the effects of both valves so that the cumulative effect is as constant as we can have it. So let me put this back to 5% here. I'm going to bring my trend up. I know there's a lot going on here. So let me just see if I can move that over a bit, trying to ignore that. And I'm going to do the same thing here. And ignore that clutter. Okay. So now I'm going to go to, let's say 15%. So you can see here, increase to 15%. The little valve, the green line here, opened up quite a bit. And then even the big valve started opening up a little bit as well. So we're now starting to open up both of them in hopefully in a coordinated fashion to make sure that then throughout the range, we can actually have a more constant process response. And that's the idea behind this. So it's not only here asymmetrical, you can see here, I'm opening it sooner on the big valve, but at the same time, I'm also overlapping both of them. So here, if I go to 25%, And now the little valve is already at 92% open. So we're almost done with the little valve, and the big valve is taking over. And that's what I wanted to show. And now I can increase, obviously, if I continue to increase the output, we're done with the little valve. It's going to go to 100%, and now all the modulation will be done with the big valve. So if I just show you here, you can see this is where we are here. The little valve is almost done, and we still got a lot of modulation here on the big valve. So if I go here, if I show you the similar response that I took from 5% all the way to 100%, you can see here even around the 50% transition right there is that the responses are reasonably constant. So therefore, it will make control tuning more robust. Remember, your tuning parameters have to match your process. And what we're trying to do here is to make the process as constant as possible. So therefore, we don't have to worry about our tuning being off, being at one end or the other end. If I go back to here, obviously I could tune it here, but then the tuning would be very different for here and vice versa. So that's why we're trying to do here is to achieve a constant response throughout the entire range. Okay, so let's go case number 3. So case number 3, both valves are the same size. Let's say they're both 4 inches. So they both have the same flow curve, but you can see here at 50% for valve 1, it is at 100%, and at 50%, valve 2 is still closed. So you can see here, you can imagine here that you might have a bit of it might be disjointed around 50% because one valve 1, is already kind of given up the ghost, and valve 2 is not even opening yet. And you can see that if I go back, so if I go up at 35%, let me cancel that, go back to here. Once again, I'm going to try to get rid of the clutter. So what's going to happen, we're at 35%. Let me see, I might go to 45%. That means now valve 1 is almost fully open. So we're at 45%. We're almost here. The valve 1 is going to give up the ghost. We're going to flatten out on our flow characteristic. So what's going to happen now, I'm going to go to 50%, which is kind of no man's land. And obviously, valve 1 goes to 100% flow. We're getting very little flow change here because we lost all our modulating capabilities. And now I'm going to go to 55%, which is going to open up the second valve. And you can see the second valve now is opening up, and we're getting a larger flow response. Once again, because now there's no overlap, there's going to be a difference, a change in the process response, which will affect your tuning. So if I go here, if I show you the similar graph, this is where you can see here no man's land right there, where obviously if you're operating around here, you're not really controlling anymore because one valve has given up the ghost and the other one is barely open. So that's why we need to have an overlap in order to mitigate that, to try to smoothen that disjointedness to make sure that the tuning then will be effective throughout the whole range. And that brings us to case number 4. So case number 4, I do have the first valve goes from 0 to 60% to 100% flow. Valve 2 starts to open at 40%. So instead of opening at 50%, it's opening at 40%. So that's the overlap here between the two. They have an overlap. So as valve 1 starts to lose the modulation capabilities, the flow modulation, valve 2 is there to help out, to kind of compensate for it. And hopefully if we adjust this properly, and listen, it doesn't have to be plus or minus 10%. It doesn't have to be, it could be anything you want, so long as the objective is to make sure that the flow response, the flow sensitivity is as constant as possible throughout the entire range. So here, if I go back to, let's say I'm at 55%. So 55%, you can see one valve is already at 44% here, valve 2, and the other one's almost fully closed. Now, if I got to close that, let's say I go to 50%. So 50% now, one valve's closed a little bit, that one closed. Let's see how that responded here. So the majority of this flow change now will have been caused by the change in valve 2. So if I go to 45%, valve 2 will start to close more, and the flow will go down. So then again, the majority of your flow changes is caused by the second valve at this point. If I go here to 40%, so now valve 2 is completely closed, but now valve 1 is just starting to get into its modulation capabilities. So I'm going to do this backwards. And if I go to 35%, so now we're really getting to the modulation capability of valve 1. And hopefully where that split, that overlap exists, was going to even out and prevent that disjointedness between valve 1 and between the transition between valve 1 and valve 2. So if I were to show you the similar curve here, you can still see there's still a bit of change right there and during the overlap, and perhaps then maybe we need to readjust that overlap. But it certainly is better than what it was before. That means now between 40 and 60%, you still have valves modulating between, so that therefore we can even out the process response between the two. And that kind of concludes that live demo. Now, one last thing before we go to our Q&A, and I already have some questions. Thank you very much. Is called mid-range control. So this is not split range, it is mid-range control. So let's consider this scenario. So we got this tank and we're adding caustic. We're going to base load the caustic into the tank, and then we're going to control the caustic, the pH. And typically this is a smaller valve. Let's say that's a 1-inch valve, and that could be a 4-inch valve. And I can't write either. That's a 4-inch valve. And so we will control the pH using a smaller valve because we got finer modulation. We can get finer control using the smaller valve. And I'll call that one little brother. But the production throughout here can vary quite a bit. It can vary quite a bit. That means there's a high turn down ratio between grade A, let's say, and grade B. We could be operating at, I'll make up a number, I'd say 100 gallons a minute going out, and then grade B could be 500 gallons a minute, a 5-to-1 ratio or a 10-to-1 ratio. And once again, trying to control the pH with that one valve can cause some issues because little brother can get into trouble. Little brother, if production rate increases, little brother goes from 50% to 60% to 70% to 80% to 90% open. And then as we saw before, we're going to lose the ghost. We cannot control let's say from 75% upward. And that's where Big Brother comes in. Because Big Brother then is going to look at the position, it's going to look at the position of little brother. And if little brother starts getting into trouble, little brother's at 65%, 70%, what's going to happen is that Big Brother is going to slowly open, very slowly open, and put more caustic into the tank. And the key here, it has to be very slowly because it will affect the process, but that will then that will cause little brother to go back into a controllable range. And that is what's called mid-range control. So the big brother looks at the position of the little brother and will adjust its output again very slowly in order to keep little brother out of trouble within a range of between 40 and 60%. So I wanted to show you that as well. I know we said split range, but I want to include that as well because sometimes some applications can use mid-range, especially obviously in a small valve, big valve arrangements where it may be beneficial, but this is obviously application dependent. So you can't just say I'm going to use mid-range for everything because it probably wouldn't work, especially if it's two valves the same size. It wouldn't be beneficial. And we're done. So here we actually have for next webinar, December 15th, will be dead time compensators. We're coming up to the Q&A, by the way. Dead time compensators. So therefore there we're talking about special controllers that can, because a PID controller is a very impatient beast. So we can develop some algorithms to be able to compensate for the time delay in the process. So therefore we can achieve perhaps some better control. And I'll be exploring that in my next webinar. And now I invite your questions. I understand that there is a 10-second time delay, so I'm going to be quiet. So someone actually wants to have a link to all my previous webinars, and certainly, yes, I will be sending you those links to you as well. Thank you very much for your interest. The one question here, what does a splitter look like? Is it used electronic parts or would it be housed within the control cabinet or in the junction box closed? So if we're talking about doing the splitting outside your DCS, it would be it could be a few things. It'd be one analog output, potentially to two positioners in series. Now, once again, you got to be careful there because some positioners have a very high input impedance, like the DVC, Fisher's DVC has a very high input impedance. And therefore, if you put two positioners in series, there may not be enough power to actually power up both those positioners. In that case, you would take one analog output, and then you can actually buy these current repeaters that then would have two 4-20 that would repeat the 4-20 coming out of your control system. And that could go to your valve 1 and that can your valve 2. So one other question, what about when you have one valve opening and the other closing, i.e. nitrogen blanketing? That's a very good question. So the idea here is the fact that you want to control pressure. And you have one valve feeding and one venting. And depending on what the pressure is doing, you got another valve right here. And again, I cannot draw. So in that case, what you would do is probably it'd be more of a V shape. So there's your curve. It'd be V shape. Could be like that, or could be the opposite, depending on which valve you want to open up first. It would be a V-shaped curve. Now the question is, there's always a bit of debate. Should it be a V-shape, one like this and the other one like that, where at some point both could be open, which is kind of a bit of a waste? Or can it be, and I'm going to run out of room here, one like this, like that, and like this, where there would be a bit of a dead band? You would have to consider all three scenarios and see which one would be best for you. But obviously, this would be done within the DCS, and but you would have to consider which one of these would be better, because obviously here, if you're 50% output, both these valves are closed. In this exact here, both valves are open, and again, that could be a waste of nitrogen. And so, depending on your control consideration, control requirement, perhaps this one or this one may be uh, better than using this scenario here. And again, a lot of scribbles there. Excellent question. Let me see here. So another question, can the big brother be an on-off valve? So let me go step back to here. And the answer is, actually the answer is just like a lawyer answer. Yes, it depends. So this could be an on-off valve so long as it is a duty cycle valve. So what happens is that this could be an on-off valve. So big brother could be an on-off valve. And let's say it has a cycle of 10 seconds. So that means that 100% that valve is open for the full 10 seconds. If the output is 50%, that means the valve will be open 5 seconds and close 5 seconds. If the output is at 10%, that valve, big brother, will be open for 1 second and close for 9 seconds. So the answer is yes. However, you got to be careful here is that you're actually going to be pulsing the flow into here. You have to ensure that you have enough volume and agitated volume to be able to smooth out those pulses of caustic going into that tank. Another question. In the mid-range control, can you transfer control from one valve to the other? I guess you could. I'm not sure why, um, unless there's a failure of some sort. So if little brother fails, then you can go control here. But obviously, you would have to change your tuning because the dynamics, if you were to control here, would be very, very different if I'm controlling from here. The reason why I like to control using the little valve is that I get a less time delay and a faster responding process because I don't incorporate any of the mixing dynamics within the tank itself. But I guess the answer is yes, you could do that, probably from a failure point of view. Is a mid-range like a decoupler? That's a very good question. So the answer is no. A decoupler, if you go back a couple of my webinars, I did a webinar on feed forward control. If you remember a feed forward control, what it does is that you got a PID controller. Let's say we got our pH controller here, and I got my flow measurement here. And what we could do is that we know that every time the flow goes up, it will affect the pH. Therefore, every time the flow goes up, we should add certain amount to the valve because we know that disturbance is coming in. So that is a feed forward control. A decoupler is a double feed forward. So if you have a pressure and the flow controller together. So any changes made by on the process line. So any changes made by a pressure controller affects the flow, and any changes on the flow affects the pressure. And so what a decoupler does there is that it will actually, it's like a double feed forward. If flow control has a problem, it will change the flow control valve, but make the equal and opposite change on the pressure control valve so that the pressure does not see any disturbance, and the opposite happens. So long answer, but the answer is the mid-range is not a decoupler. Seems to be that overlap in general is a better configuration. Is this true in all use cases? Not necessarily. As I just went through before for the nitrogen, as we talked about before, it may be useful not to have an overlap. It depends on your control requirements. So not all cases do you need an overlap. These are great questions, by the way. So another question, is the split done in the DCS output from two analog outputs? And the answer is yes. You don't have to, otherwise you would have to do the split at the positioner or at the I2P if you're using one. And as I mentioned before, it's certainly a lot more um, flexible and visible to do the split in the DCS and provide two separate analog outputs to each valve. And that was the last question. I'm going to pause again to see if there are more questions. Those are great questions. Thank you very much. So I'm still going to pause here for another 30 seconds, see if there's any more questions. So one question here. Good. Then in the case of Big Brother, being an on-off output of the ZIC is time? Correct. So I see this. I've been actually going to be working for a pharmaceutical company this weekend. Yay, lucky me. Where they actually do pH control, and it's based on this duty cycle. So once again, 0 to 100% is 100% opens up the valve completely, the on-off valve. This is inside a fermenter. And at 50%, the on-off valve would be open for 5 seconds, closed for 5 seconds, assuming a 10-second total time. And I got a message there thanking me. Thank you very much. Yes, you will be getting a link to the recording of this webinar. And as I mentioned, if you think of a question afterwards, you're more than welcome to reach out to me via email or by phone, by cell phone. Just going to pause a little bit longer here. So another question, if we go with position or I2P converters configuration for split range rather than DCS, do we have this flexibility for overlapping or mid-range? You do have the flexibility for overlapping, so long as if it's a digital positioner, you program it in. If it's an analog positioner or an analog I2P, that you calibrate it properly. So yes. For mid-range, no. A mid-range is strictly done within the control system. It is strictly done within the control system. It is a control strategy. So it sounds like I still got question trickling in. All right, I'm just going to pause another. No, another question. There we go. So the question is, when do we decide to have each configuration during basic engineer control system configuration? I guess the basic engineering, the process design is going to dictate whether or not you need split range. So based on your process design, do you need two valves because you got a very high turn down ratio? That's pretty much the process consideration to determine whether or not you need two valves or not. So that's the first thing. And then after that, obviously, is the control philosophy. Now we got two valves to handle it. How are we going to do it? That would again be done probably in basic configuration or even during the control narrative design. So this is great. You guys are really responding here. Really appreciate it. Thank you very much all for attending. I got another question here. Is split range control a good solution for temperature control in steam application too? I would assume so. Yes, it depends on your application. Uh, Sometimes I can certainly imagine certain scenarios where you may need to have split range. Absolutely. So the other question: how can I simulate before putting it in service? Uh, we could talk about that later on. We can talk about that, how you can simulate it within your DCS. And obviously simulations, I always talking, they're like fractals. You can go to the infinite detail or way out macro detail. But yes, you can simulate it within the DCS or whatever simulation software you have. So I got another question here. Well, it's a long one here. So I got to make a vent system on a pressure system loop. At low pressure, A opens to import nitrogen while B is closed. On high pressure, A is shut, B opens to flare. Considering percent alpha, it made the tuning much smoother. Especially the impact on the other loops was huge. My question is there a method to pick an overlap, or is it based on experiment? That's a good question, actually. And once again, give you the lawyer answer. It depends. I would say probably a little bit of both. If you can model, if you know your process conditions beforehand, and you can maybe simulate it or understand your flow rates, you could probably try to do it over ahead of time and try to mitigate a little bit some of the experimentation. But I think at the end of the day, probably experimentation and data collection and data analysis is probably the way to actually establish a proper overlap. These are great questions. Incidentally, we have people here from two continents. We have people from South America attending this as well. So it's one of my larger attended webinars. So I appreciate it. Thank you very much. Again, I'm going to pause again. Seems to be some more questions coming in. And so those of you are asking for my email, I think I had it at the beginning of the webinar. It's 𝗠𝗢𝗓, 𝗠𝗢𝗓 𝗦𝗓𝗡𝗢 at lakesidecontrols.com. And you can also we're actually all recording your questions and everything else as well. So I can actually send out an email. So, okay, I'm going to pause it for now. There seems to be no more questions. As I mentioned before, if you do have questions later on, you are more than welcome to email me, and I will get back to you. You will be put onto a evaluation page. Certainly would like to make sure. Please give us your feedback. As I said, good. There's no such thing as bad feedback. Feedback is always good. So thank you very much. Uh, Yes, I now will. Like I said, you will be getting the links and so forth, and we will be forwarding you the links to the webinar. Uh, so no, yeah, someone's actually asking a question about my next webinar. So, the Smith bridge is used to overcome dead time. BID is hard to overcome dead time. Yes, that's right. That will be my topic for next December 15th. We'll be talking about the modified Smith predictor, not just a Smith predictor, the modified Smith predictor. So, all right. Another question, actually, so it still keeps on coming. All right. What is the flow economy limit to use split control? I'm not exactly 100% sure what the question is, but if you say we would get finer control using two valves than using one big valve. As I mentioned before, if your turn down operating ratio is, I say, that would cause a one valve to operate at 10% and at 90%, you would not get very good control at those extreme ranges. And that's why we use split range. And you get finer control. Yes, you have to buy two valves, but you do get finer control and probably gain some economic benefits from an operating strategy. So I'm still going to wait here. Obviously, questions are still coming in. So another, is there a magic number on the ratio between sizing of the two valves? Yes, it's I can't remember now. It was what's the magic ratio number that Leonardo da Vinci had? No, there is no magic number. There is no magic number. It depends on the process requirements and the pressure drops, and so forth. So there's no. I mean, typically maybe a 2-to-1 ratio, 4-to-1 ratio. I can't imagine anything higher than that, like a 1-inch valve and a 10-inch valve. That wouldn't make sense. But 1-to-2, 1-to-4 ratio is probably reasonable. Again, I'm still going to pause. Okay, we're coming up until lunchtime. Certainly want to thank all of you very much. This has been a great success. And certainly hope to see you on December 15th for Dead Time Compensators. And I really, really appreciate all of you. This has been a record attendance for me, and record attendance geographically and numbers wise as well. So certainly want to thank all of you for attending. And always feel free to reach out to me. And I'll make, so if you have any further questions or comments or need assistance. Thank you very much, all. You guys be safe, and hopefully I'll see you December 15th. Thank you.